My name is Mitchell Easley. I'm a researcher for the Power Electronics and Autonomous Systems Research Group, and I will be discussing my research on reactive power injection techniques for grid-connected photovoltaics at the distribution level. Before going into the details of my research, I think it's important to provide motivation for this research area from a high level, and a good example is the Northeast blackout of 2003. This was the largest blackout in U.S. history. It affected many states and parts of Canada. In most areas, this blackout endured for several days, and the financial cost of this event was on the scale of billions of dollars. In the aftermath of this blackout, a U.S.-Canada joint task force was formed to investigate the causes of this blackout and make recommendations for the future. Their research and findings are documented in a final report. And although there is not a single cause of the blackout, a dominant source of cause of this blackout was inadequate reactive power injection, or in other words, the starting point of the blackout, which exposed weaknesses in the grid's communication infrastructure, was inadequate reactive power injection. So there's definitely motivation to research reactive power injection techniques at the distribution level, especially with the steady increase of feasibility in photovoltaics. So in my research, I use a single power stage solution for grid-connected photovoltaics, the quasi-impedance source inverter. The energy storage components between the input and output of the converter allow for using shoot-through states, which create unique and useful dynamics for the input current. I am using a 4-quadrant programmable AC source to act as the 120 volt, 60 hertz grid in the hardware experiment. In this video, I demonstrate the controller's ability to seamlessly transition into low voltage ride-through mode, where the controller senses a voltage sag and injects reactive power. Currently, the system is in maximum power point tracking mode, with the capacitor 1 voltage regulated at 275 volts. In the oscilloscope, the yellow signal is injected grid current. The light green signal in phase alignment with the grid current is the grid voltage. The light blue signal is capacitor 1 voltage, and the red signal is the input current to the quasi-impedance source module. At this point, the grid voltage sag has occurred, and the controller responds by injecting reactive power to the grid, which is evidenced by the grid voltage leading the injected grid current. With maximum power harvesting maintained, the reduction in grid voltage has increased the active current reference, along with the non-zero reactive current reference, leading to a notable increase in the current amplitude. Now the grid voltage has returned to normal condition. The inverter quickly adjusts its phase to align with the grid voltage.